How to 3D print human tissue. There are currently hundreds of thousands of people on transplant lists, waiting for critical organs like kidneys, hearts, and livers that could save their lives. Unfortunately, there aren't nearly enough donor organs available to fill the demand. What if, instead of waiting, we could create brand new, customized organs from scratch? That's the idea behind bioprinting, a branch of regenerative medicine currently under development. We're not able to print complex organs just yet, but simpler tissues, including blood vessels and tubes responsible for nutrient and waste exchange, are already in our grasp. Bioprinting is a biological cousin of 3D printing, a technique that deposits layers of material on top of each other to construct a three-dimensional object, one slice at a time. Instead of starting with metal, plastic, or ceramic, a 3D printer for organs and tissues uses bioink, a printable material that contains living cells. The bulk of many bioinks are water-rich molecules called hydrogels. Mixed into those are millions of living cells, as well as various chemicals that encourage cells to communicate and grow. Some bioinks include a single type of cell. Others combine several different kinds to produce more complex structures. Let's say you want to print a meniscus, which is a piece of cartilage in the knee that keeps the shin bone and thigh bone from grinding against each other. It's made up of cells called chondrocytes, and you need a healthy supply of them for your bioink. These cells can come from donors, whose cell lines are replicated in a lab, or they might originate from a patient's own tissue to create a personalized meniscus, less likely to be rejected by their body. There are several printing techniques, and the most popular is extrusion-based bioprinting. In this, bioinks get loaded into a printing chamber and pushed through a round nozzle attached to a printhead. It emerges from a nozzle that's rarely wider than 400 microns in diameter and can produce a continuous filament roughly the thickness of a human fingernail. A computerized image or file guides the placement of the strands, either onto a flat surface or into a liquid bath that will help put the structure in place until it stabilizes. These printers are fast, producing the meniscus in about half an hour, one thin strand at a time. After printing, some bioinks will stiffen immediately. Others need UV light or additional chemical or physical process to stabilize the structure. If the printing process is successful, the cells in the synthetic tissue will begin to behave the same way cells do in real tissue, signaling to each other, exchanging nutrients, and multiplying. We can already print relatively simple structures like this meniscus. Bioprinted bladders has also been successfully implanted, and printed tissue has promoted facial nerve regeneration in rats. Researchers have created lung tissue, skin, and cartilage, as well as miniature semi-functional versions of kidneys, livers, and hearts. However, replicating the complex biochemical environment of a major organ is a steep challenge. Extrusion-based bioprinting may destroy a significant percentage of cells in the ink if the nozzle is too small, or if the printing pressure is too high. One of the most formidable challenges is how to supply oxygen and nutrients to all the cells in a full-size organ. That is why the greatest successes so far have been with structures that are flat or hollow, and why researchers are busy developing ways to incorporate blood vessels into bioprinted tissue. There's tremendous potential to use bioprinting to save lives and advance our understanding of how our organs function in the first place. And the technology opens up a dizzying array of possibilities, such as printing tissues with embedded electronics. Could we one day engineer organs that exceed current human capability and give ourselves features like unburnable skin? How long might we extend human life by printing and replacing our organs? And exactly who and what will have access to this technology and its incredible output? Thank you for listening.